So if we talk about the LCR circuit and specifically talking about series LCR circuit here, where LC and R all three are connected in series and we do have a voltage source. Such circuits are applicable in making a radio. The cheapest radio that you can make will be within 15-20 rupees you can make, because you can get these components, make a circuit and actually try to get hold of a signal. We may talk about radio, how does the tuning work and all later. But for now, this is the series LCR circuit that is there. It has got a lot of applications, and just going to analyze this. Now, if you talk about a series LCR circuit, what is the voltage across this will totally depend on LC and R. Okay, so for that, what we do is we specifically find out the voltage across VL, VC, and VR, which we already know from our previous lectures, and we are going to plot it in the phasor diagram, and then we are going to do our calculations. So I've drawn here a series LCR circuit, and let's say a current I is equal to I naught sine omega t is flowing through it. Now, if you write down the relation for the voltage for such a circuit, uh, you know that the voltage and the current are in phase for a resistor. So VRT would be V naught R sine of omega t. There is no phase difference. So it's same as this sine omega t. This is also sine omega t. If you talk about a capacitor, okay, sorry, an inductor, this should be an inductor, not a capacitor. If we talk about an inductor, we know that the current is lagging the voltage, right? The current is behind the voltage, and how much it is behind the current is pi by 2 behind voltage. That means the voltage is ahead by pi by 2. So that's why I've written it here as sine omega t plus pi by 2. For a capacitive circuit, we know that the current is ahead of voltage. That means the voltage is behind the current. So that is omega t minus of pi by 2. Now, based on these three, we can actually draw our phasor diagram, and we already know that the voltage is I naught R for resistor. For the inductor and capacitor, it will be I naught into the inductive reactance and the capacitive reactance, right? So we also know that if we talk about the capacitive reactance, it is 1 by omega C, and XL is equal to omega L. Okay, so these things we have already done before. We're just going to draw the phasor diagram now. Now, if you look into the phasor diagram, what are the parameters for voltage that we are going to draw along the x-axis and the y-axis? So let's say the current is flowing along this axis. Okay, let's say the current is flowing along this axis. That means the current and voltage are in phase only for resistor. So that means for a resistor, I can draw the voltage across this. That is R. If you look into this, we already know that if you're going in the anti-clockwise direction, that means we are going towards the positive axis, right? Or we are going to plus pi by 2. So here plus pi by 2 is this, so V naught L. So we can write it down as V naught L along this axis. Now, if I just look into the capacitor, the voltage is behind the current, right? So behind means we have to go in the clockwise direction. So that means what we can do now is we can actually write another axis, which is the negative y-axis, okay, and we can actually draw our voltage across that, right? So that would be the voltage for the capacitor. So this is the phasor diagram for the voltage, okay. So in a similar way, we can also draw the phasor diagram for the current, right? Or we can draw it for the reactance also. So let's draw the phasor diagram for the reactance. And when we draw these pictures, we do understand that uh, they will actually give me a clear picture of what is exactly happening and what is the relation between the voltage and of course the reactance between the three quantities that we have. So if you're talking about the reactance, okay, we know that the resistance will be along this. Okay, the resistance will be along this, right? The inductive reactance will be along this, and the capacitive reactance will be along this, right? We can simply use this relation. In place of V naught R, we can write down I naught R, V naught XL, I naught XL, V naught C, I naught XC, I naught will be common, so we can cancel them out, and we'll be actually having the phasor diagram something like this. Okay. Now, if you look here, there can be three kind of cases. Okay, let's discuss the cases one by one. But before that, what are the cases possible? The first case might be that this V naught L and V naught C are different. That means, let's say V naught L is greater than V naught C. The second case might be V naught C is greater than V naught L, and the third case are both of them are equal. Okay. What do you mean by greater than? Greater than means that this entire circuit will have more effect of the inductance compared to the capacitance. Okay. So if you look into inductance, the voltage is ahead. That means for the entire circuit, if we consider, the voltage will be ahead. Okay. So in this, we can actually consider three cases, and let's take one by one. Okay. The cases, it's very simple. First case, okay, case is number one. So if we take the first case, we can say that this V naught L that we have, or the inductor, let's say it is greater than V naught C. Obviously, the inductance is more, okay. So we can also say that the inductive reactance would be more compared to the capacitive reactance. Okay. In such a case, even if it's an LCR circuit, we say that the effect of inductance is more, so we can call it as an inductive circuit. It's not a purely inductive circuit, it's an inductive circuit because the effect of inductance is definitely going to be more. Okay, now we can again draw our phasor diagram. Okay, we can again draw our phasor diagram, and for drawing that, something like this, right? And we know that my V naught R is in this direction, V naught R is in this direction, uh, V naught L was in this direction, that we already know. Okay, but now I want to find out what is the effective voltage, right? What is the effective voltage? So if you look here, this is V naught C, this is V naught L. V naught L is greater than V naught C. That means the resultant direction will be in the direction of V naught L, because V naught L is greater than V naught C. Okay. So if you look into the vector, and if you remember vector addition and subtraction, the resultant would be V naught L minus V naught C, and the direction would be towards V naught L, right? So that means the resultant would be V naught L minus V naught C, and as per vector, the direction would be in the direction of the greater vector. Okay, so that is how we can actually draw this diagram here, right? So that means this is my inductive circuit, and now what I want to find out is this. What I want to find out is this V naught. What is this V naught? Okay, the peak voltage for the entire circuit. So you see that V naught L minus V naught C and V naught R are making an angle with each other. So if you want to find out the resultant of that, since both are vectors, we can actually find out the resultant. Okay, and this resultant would be the peak voltage. This resultant would be the peak voltage. Okay, so this is basically nothing but vectors. Okay, and this is making an angle of phi, the same angle that we are interested in. Okay, right now it cannot be 90-degree addition or subtraction, because V naught L, V naught C both are there, even R is also there, so there is a combined effect now. So if I now want to find out what is the resultant, I can simply take V naught square is equal to V naught R square plus resultant. So these two are together now. So let me just take it as V naught C plus V naught N. Please remember, we are doing the vector addition of the peak voltages. Okay, so that's important. Not plus, minus. Uh, V naught L is greater, so I'll take this before V naught L minus V naught C. Okay, so we can do that, and we already know what is my relation for. So we already know what is my relation for the impedance. Okay, we have done it before, so we can take that as well. Just a second. So what are our relations between the V naughts? It is this one, right? So I naught R and so on. So we can just write down these relations here. We can simply write it down as. So let's just replace these values here. So this is I naught square R square plus this is I naught XL minus I naught XC whole square. So we can take this as I naught square R square plus I naught can be taken out common. This is a square, so I'll take I naught square, and this would be XL minus XC. Okay. So again we can take I naught square common within bracket. It would be R square plus XL minus XC whole square. Right. So you can take it like this, and this was V naught square. So I want to find out what is my V naught. That's what I'm interested in. So I can simply write it down as V naught is equal to root over. So I naught square will become I naught, and on this side I will have it as square root of R square plus XL minus XC whole square. Now you know this is voltage, and voltage is equal to current into resistance. Here we have components of inductor and capacitor, so that means it won't be resistance, it would be reactance. So I can simply write it down as I naught into Z. So this Z is my impedance, right? So this is something which you already know. So this ZB that we have is equal to, this is going to play a very important role for different kinds of calculation, XL minus XC whole square. Okay, and this is called my impedance. We've already done impedance when we talked about the other kinds of circuit. Okay, so this is my impedance here, right? So that means if I know, now I know what is my V naught. V naught is nothing but I naught into Z, and we know what is the nature of Z here. Okay, so if we actually want to find out what is the phase angle, that also can be done, because I think we have already done these kind of problems before. If you know the impedance, we can actually take the ratio. This is my impedance diagram. Here also the same thing. In place of V naught, I can write down I naught Z. In place of V naught R, I can simply write it down as I naught R. Okay, so that means this is my R, this is my Z. Okay, and this would be nothing but my XL minus XC. Do that. Okay, so even if you look into this phasor diagram for here also, we can actually see that Z will be equal to root over of R square plus XL minus XC square. Okay, and even if we replace it here, then also we are going to get the same thing. So that's very important. In a way we can do it, right? In a similar way we can also find out what is my phase angle phi. Okay, so if I want to find out what is my phase angle, tan phi. Okay, so tan phi would be uh, this minus this axis. So we can drop a perpendicular here, right? This was my XL minus XC. So that would be nothing but XL minus XC divided by R. So if you know what is R, if you know what is XL and XC, you can easily calculate what is the phase angle. And if you calculate the phase angle, you can write down that final relation for V naught. Okay. So that was my first case. In second case is also very simple. Okay. It's just the reverse. Okay. If we are not going to do it in detail, I think it's very simple here. Case 2. Case 2 is this V naught phasor diagram. You have to be very careful when you draw. V naught C is greater than V naught L now. V naught L, okay, or XC is greater than XL. So this is my capacitive circuit now. That is the second case. So if you go for the second case, and if you actually want to draw the phasor diagram, what you can do is current and voltage, but this time the capacitive circuit, right? So you can see that the capacitance was going down, right? The voltage for the capacitance, peak voltage, and we have got a V naught L. It's in the direction of V naught C, and it will be V naught C minus V naught L. So we can take it like this, and I can write it down as V naught C minus V naught L, and this would be nothing but V naught R, right? So that's it. So you can do it for current also, the same thing, the same logic will follow here, okay? And if you do this similar calculation, okay, what we are going to get here is this V naught is equal to, okay, we are talking about this V naught, right? This V naught, same vector addition, okay, and so on. So this would be uh, I naught root over r square plus, now this time xl is not greater than xc, xc is greater than xl, so it would be xc minus xl square, okay. So that means my z is going to be root over r square plus xc minus xl whole square, right? Now again, you see, whether you take XL minus XC or XC minus XL, since it's under square, this is not going to affect the impedance. Okay. So what does it mean? That whether you have V naught greater than C, V naught C greater than V naught XL, or V naught L greater than V naught C, in both the cases, the impedance is going to be the same. Okay. And if you draw your phasor diagram for the reactance, the Z or the tan phi will also more or less be there. Okay. You can also calculate your can find this particular case, okay. So that is also possible. So if we just, okay, let me just complete this. So if we take out 10 5, okay, that was xl minus xc, here it will be xc minus xl, whichever is greater will be at the front to make it positive or keep it positive, right? So you can take that. So you can find out 10 5, you can find out z and so on. So it's not complicated. So if we are thinking of this, whether v naught L is greater than V naught C, or vice versa, Z will always be the impedance and it will remain as R square plus XC minus XL or XL minus XC whole square. So this is going to remain the same. Okay. This brings us to case 3. Okay. Case 3 would be that both of them are equal. Okay. Both of them are equal. So that means we can say that V naught L is equal to V naught C, or XL is equal to XC. Now, if XL is equal to XC, we're really not going to do any kind of calculation here. We can just simply see that XL and XC are equal. XL and XC are equal here. Here, both of these vectors are going to cancel out each other, right? So that means the circuit will be more or less a resistive circuit. Okay, it will be a resistive circuit. Remember, XL and XC are not zero; they're equal. Okay, so that means Z will be equal to root over of R square plus 0, which is equal to R. So this will become a resistive circuit. Okay, so when this becomes a resistive circuit, this is actually called the resonant condition. So what do you mean by resonant condition? See, what happens is, if you're considering a radio signal or something like that, the interest is that you should get maximum current. Okay, maximum current, or sorry, maximum voltage, right? So when we're looking into the peak, we can actually see what will be the condition of maximum voltage. So we already saw that V naught is equal to I naught divided by Z, right? If you look into any of these cases now, and if you want to know what is, sorry, I naught into Z, right? Sorry, let me write down the relation first. V naught is equal to I naught into Z. So what happens is that if the resistance is if the impedance is more, you're going to get more voltage, right? So if you just want to find out what is my current is v naught divided by z, right? So in this particular case what happens is that if z is less, your I naught would be more. Okay, now z is least when z is equal to r. That means you're going to get current maximum, or what can you write down as current is going to be maximum. So the condition for maximum current is at the resonant condition. So what happens is if Z is minimum, that means at resonant condition it will be R, which is minimum. You are going to get maximum current. Okay, and that is the condition that we are going to use to do some calculations as well. So Z is equal to R. So this is my resonant condition. Obviously, in resonant condition there are different things that we need to do, but we're going to do that later. Okay. Now what we're going to do is let's just do one sum here. Okay, quickly one sum. I will take up one circuit here quickly. Okay, so let's say there is this value, there is a resistor, there is a inductor, a capacitor. Voltage source. Okay, let's say R is equal to 3 ohm. uh, let's say L is equal to 0.16 Henry, and C is equal to 500 microfarad. Okay, we don't know what is V, one of part of the question. I is given to be, let's say, 10 sine of 100. We're just going to practice this one problem. Okay, what you have to do is you have to find out one by one. Excel, we can do that. XC, Z, impedance, phase difference. Okay, number 5, let's say peak voltage, the relation for this VT. What else we can find out? VRT, VLT. So you cannot have a question more than that. Okay, or everything we are including here. So you can definitely try to find out all these. VCT, power factor, power. Whenever someone says power, means you are supposed to find out the average power. Okay, so we have to calculate these factors. Okay, power factor also we have discussed. So if you just look here, XL and XC, that's simple, right? Let's just do it one by one. Okay, it's not going to take time, obviously. This is omega into L. Okay, omega is already given 100. L is 0.16. So if you just multiply, that's nothing but 16 ohm. Right? I'm just doing it directly. Don't need to do much calculations here, I guess. XC is 1 divided by omega C. So omega is again 100. And my C is 500 microfarad, right? So I can simply write it down as 1 divided by 100 means 10 square. And 500 has 2 more zeros, so it is 10 to the power 4. Right? Into 10 to the power minus 6. Right? So that's there into 5. So what would be this? Minus, so it will be 100 divided by 5. So this would be 20 ohm. So we've got XL is this, XC is this. So we can find out what is my Z, right? So Z is equal to root over of v square plus xl minus xe, so that's 20 minus 4, so that's 4. So you can write it down directly, 4 square. 9, 16, 25, so it is 5, right? So most of the time these questions will be like this, that you will be getting these kind of results. Next we have to find out phi. Now if you want to find out phi, that means you have to find out what is sorry, tan of phi, right? Tan of phi, tan of phi. So you can just check whether it's a capacitive or an inductive circuit. Capacitive reactance is this is 20 and this is 16. So obviously X is greater than XL. Okay, so you can check this. If X is greater than XL, that means we have to write it down as XC minus XL divided by R. So 20 minus 16, so that's 4 divided by 5. Okay, for convenience, you can remember this diagram. This this is actually, this value is used a number of times in physics, so that's why it's important. This is 53 degree. Okay, and you can look into the sides. You can just simply write it down as this is 3, this is 4, this is 5. Okay, if you remember this diagram, you can find out what is tan 53 degree. Okay, very easily. So if you check here, phi tan 53 is 4 by 5. See, 4 by 5. Okay, sorry, this is ulta I've written. This is 3, 4, 5. Okay, so perpendicular divided by base, so this is 4 by 5, so that's 53. Okay, you can remember it like this. So phi is 53 degree. So that's my phase difference. What else we need v naught. Okay, so v naught is the peak voltage, is nothing but I naught into z, and I naught is given to be 10 because this is 10, so this is 10 into z is 5, 50 volts. What else? Vt, right? So Vt, now it's almost done. If we talk about Vt, it will be nothing but v naught into sine of omega t. Now whether it will be a minus or plus will be depending on whether it's a capacitive or an inductive circuit. We know it's a capacitive circuit. In a capacitive circuit, okay, if you just look here, written once, yeah. So if you look into a capacitive circuit, the voltage is behind current, the current is ahead of voltage, so it is minus, always minus, right? So if it's a capacitive circuit, it will be minus, so it will be minus of 5. Now we know all the values here. V naught, we've just calculated. Where is it? This one, 50. That's 50 sine omega. We can see it from I naught itself, right? This is my omega 100t, so that will remain as 100t minus 5. 5 is 53. So this way you can actually calculate these values. V naught is already done. Then you have to find out what is VR, VL, and VC. Okay, that's quite simple because when we're talking about VR, that means we are not considering the capacitive and the inductance. So that means this will actually remain as V naught sine of omega t, right? So that will be 50 sine of 100t. Similarly, you can do it for VL also. VL is V naught sine of omega t, but this time it is only VL. There is no VC. Afterwards, find out what is the voltage across VL. So we can simply write it down like this as pi by 2. This will be pi by 2. The combined effect is 5, but individually it's not 5. Right? Similarly for VC. Minus of 90. Okay, so almost done. I'm just going to discuss a bit about, you know, power factor. So sorry. So what happens is if you're basically considering a power in an AC, you can write it down in the different forms. Okay, let's just quickly discuss about power factor since we have not discussed this before. Just missed out on this power factor. So we do know what is power, right? Power is equal to voltage into current. Power P is equal to V into I. Now, whenever we write down V into I, we know what is my V. V is equal to V naught sine omega t, right? And I is equal to I naught sine of. Let's say I don't know whether it's a resistive circuit or capacitive or inductive circuit. So definitely there will be some phase difference. So let's say this is my I. So if you just write it down here now, if I just want to write down what is my power, I can simply write it down as V into I. So V is nothing but V naught. Let me take V naught I naught. So V naught I naught sine of omega t sine of omega t plus phi. Okay. Now this power that we are actually going to see here, whatever we are seeing here, is actually the instantaneous power at any instant. Instantaneous power at any instant, at any point of time. And this is quite insignificant because when we are considering a circuit, we more importantly we should know what is the average power and not the instantaneous power. Okay, so we can actually calculate the result for instant average power. We have already seen the formula for finding the average voltage and average current. Okay, similarly we can also find out what is the value for average power. So we have discussed this before, that if you want to take the average over time for any quantity, you can simply use the relation P average is equal to integration for the entire time cycle. Okay, P dt divided by 0 to t dt. So this way you can actually find out what is my average power. We can put in the result here. I use the trigonometry and try to find it out. There are other ways of finding it out as well, right? We can just talk about the average, something like this. You can simply write it down as this. Okay, let me write it within the angle bracket that will represent average, or I can also write it down like this with a bar, right? So if we do that here, we know what is this V naught I naught sine omega t plus phi. So if you want to actually find out the average for this, we can write it down as, let's say, V naught I naught sine omega t, and here it is sine omega t plus phi. So sine A cos B cos A sine B. So we can take that as sine omega t cos phi plus cos phi sine omega t. Okay, yeah. So we are going to find out the entire average. This average we are calculating here, right? So what we can do now is maybe V naught I naught. This is also a better way or easier way to find out the average. Sine square omega t cos of phi. We're just going to individually find out what is the yeah, average of these two quantities. Okay, cos of phi, and here we see sine omega t. Okay, sorry, I think this formula I've written it wrong. This cannot be phi again, right? This is sine omega t cos phi, cos omega t sine phi. You can write it down as cos omega t sine phi. So this is multiplied with sine omega t cos omega t. So let me write down a 2 in front. 2 sine omega t cos omega t into sine of phi divided by 2. There was no 2 before, divided by 2. So this average we have to find out now again. Okay. So that means I can write it down as V naught I naught. Let's just separate out the quantities. This average Because this is a constant, so average is going to be the same result. And this is sine square omega t cos phi. Certain results we can always remember: cos phi, average of this, plus average of this. So this is sine 2 omega t sine phi divided by 2, divided by 2, and take the average of this. Okay. So now what happens is we can actually consider these trigonometric ratios and find out their average. V naught and I naught are constant, so their average would remain the same. And if you calculate it for sine square omega t, you can use this formula. In place of p, you just put sine square omega t dt divided by integration of 0 to t dt. You can take that average, and you will find out that the result is half. Okay, into, now cos phi is the phase angle. This is phi, and this is the phase angle. That means this is going to be a constant for a circuit. So that means this cos phi is constant. So that means it does not depend on time. You can see it does not depend on time. So that means it will remain as cos of phi. On this side, if you take sine 2 omega t, you are going to get the result to be 0. The result is going to be 0. So that means my result would be half v naught I naught cos of phi. Okay. Still, this is done actually. Cos phi is actually the power factor. But as we said that I naught and V naught doesn't make much sense when we are basically considering this. What we can do is we can consider it in terms of IRMS and VRMS. So V naught can be written as V naught by root 2. I naught, let's write it down as I naught by root 2. So root 2 will become 2. So that means it remains the same into cos of phi. Okay. So that means I can take this to be V naught I naught. So this is VRMS, and I naught by root 2 is IRMS, already calculated, into cos of phi. Okay. This cos phi we actually have is the power factor. What does it tell me? It tells me by what phase, okay, the angle changes based on which the power of the circuit will actually get affected. Okay. So idea is quite simple here. Okay. In a way, we can also find out what is the average, right? So if someone tells me find out what is the average power, we can use this formula. If someone tells me what is the power factor, we can simply use this formula, right? So different kinds of circuit will have different kinds of power factor. Okay. Let's just quickly write down this. So this is important actually. Sometimes never know, might be some objective question. Okay. Circuit, what would be the value of phi, and what would be the power factor? Power factor, right? So if you're basically considering a resistive circuit, you can actually make a table for you also. You can just keep it like this. V and I are in the same direction. That means there is no phase difference. So this is 0. That means the power factor is cos of phi, cos of 0, which is nothing but 1. Okay. So what does it mean? That if you're basically writing down the average power, and I write it down as VRMS into IRMS into power factor is 1. So that means we're going to get maximum power. Okay, maximum power is possible when we are basically considering a resistive circuit. That's quite obvious, because when we talk about power, we know it is nothing but I square R. So if this I is the current, R has to be maximum. If you are considering an AC circuit, it is actually I square Z. So whenever Z maximum, okay, you're going to get that maximum power, right? So you can see here, this is my maximum power that is possible. Okay. On the other hand, if you're basically considering other kinds of circuit, let's say I consider an inductor, okay, and in this case, we know that the voltage is ahead of current. The current is lagging the voltage. Here it is by 90 degree. So the power factor is 0. Okay, minimum power I V when we are considering a capacitive circuit. So here also it is 90 degree cos phi is equal to 0. Okay. So this is the basic idea behind power factor. So based on this, if we just go into our previous problem and see what is the question. First thing is what is power factor. That means you have to just find out what is, uh, let me write it down as power factor cos phi is equal to cos of 53. You can use the same triangle to find out even for cos also. Okay, it's cos of 53 degree. So if you check it here, okay, base by hypotenuse, so it is 5 by 3. So that would be the power factor. You can also find out what is the average power now. So average power, I think it's fine. Average power is equal to VRMS IRMS into cos of phi. We already know what is V naught and I naught, so I can simply write it down as V naught by root 2 into I naught by root 2 into 5 by 3. Perfect. Right. So if we check it here, okay, okay, just wait. I think we used of did we use a formula wrong? Sorry. Just make this correction. Okay. Don't recall the triangle here. I think I've drawn it wrong. This is 5, 4, 3. Just give me a moment. Let me just check this. 5. This is 4, and this is 3. This way you can remember it correctly. Okay, so if you want to find out what is this is 10. This is XC minus XL divided by R, right? And what is my R here? R was 3. Sorry, this was not 5. R was 3. That correction has to be made. So this is 4 divided by 3. So if you look into this triangle now, trick to remember, 5, 4, 3, 4 divided by 3 would be nothing but 10 of 53. Okay. Now using this same triangle, you can also find out what is cos of 5 by 3. So you can see cos of, not 5 by 3, sorry, this is 5 by 3. This is wrong. Power factor. You have to use this formula, right? 5 by 3 cannot be greater, right? Numerator cannot be greater than the denominator because we are taking cos. Okay, the values cannot be greater than 1, obviously. So there's something wrong. 53. Okay. So base by hypotenuse 3 by 5, not 5 by 3. So it is 3 by 5. So this should be 3 by 5. Okay. So now in this calculation, have we found out what is V naught and I naught? I think we have done. Yeah. V naught and I naught, we have already done it, right? Where is it? Where is it? This one was my V naught. I naught is already given to be 10. So you can put out the values and find out what is the average power of the circuit. So that means I can use the relation for this average power, okay, and find out what is the average power. And of course, the cos phi is actually going to give me the power factor. Okay, so that's important. So if you basically consider a resonance circuit, okay, let me just take a new page here. Resonance in LCR circuit. Resonance in LCR circuit. So if you're basically considering a resonant circuit, we know what is the condition. The condition is that the resistance has to be maximum, right? The condition is that the capacitive reactance and the inductive reactance are equal. Okay. So what does it mean? It means that, see, if they are equal, we know that Z is equal to R, right? Because of this condition. So now if I write down X is equal to XL, I know X is 1 divided by omega c and XL is omega n. Okay, so let's say the frequency at which both of them are equal is omega naught. So I'll consider this to be resonant frequency. So this is omega naught, this is also omega naught, and we can cross multiply. So I can simply write it down as omega naught square is 1 divided by LC, or I can write down this as omega naught is 1 divided by root over of LC. So this is my resonant frequency, this is the angular frequency. Let's write down the linear frequency, 1 divided by root LC. So that means F is equal to 1 by 2 pi root LC. Okay, so this is my resonant frequency. Okay, so this is something which is all about resonance, and we know that at resonance we have got the maximum uh, current, because resistance is going to be minimum, the impedance is going to be minimum, that means the current has to be maximum, right? So this is the idea behind resonance. Now there are certain graphs that we should actually know in this unit. Okay, let's draw some graphs here. Objective questions, multiple choice questions are always possible. Before we draw the graph, let me just write down this. XL is omega L. If I write it down in terms of linear frequency, it is 2 pi f into L. And Xc is equal to 1 divided by omega C, which is equal to 1 divided by 2 pi Fc. Now, what we can do is, let's plot some graphs here. Okay, let's plot a graph between a resistor, okay, and frequency, the resistance and the frequency. Okay, so let's say we're talking about impedance. Okay, let me not call it as a resistance, let me call it as impedance and frequency. Now if you check here, if we are basically having for XL, frequency and XL are directly proportional to each other. Okay, so when we talk about XL, we can simply draw this, right? They are directly proportional to each other. Okay, just draw it clearly. Okay, so this would be the diagram for XL, because here we can see that the impedance and the frequency are more or less directly proportional to each other, right? On the other hand, if you're basically considering, Z is equal to, just give me a moment, I have to just throw some, I'll just come back. Okay, so what happens here is that uh, when we talk about the graph, let me just write down it as Z. Let me write it down as reactance, right? I think that would be a much better word here. It's not about Z. It depends on what you are considering, which factor you are considering. So let me write it down as reactance. So if you look here, XL, for XL, it is XL minus versus frequency. So it's directly proportional. So it will be something like this. If you talk about XC and F, it means it's inversely proportional. So that means when the frequency is minimum, the reactance is maximum, right? Sorry, yeah, and vice versa. So let's say the frequency is minimum, the reactance would be somewhere maximum, and as the frequency keeps on increasing, the reactance will keep on decreasing. Okay, and then finally, if we talk about the resistor, this is your XC. Finally, if you talk about the resistor, resistance does not depend on frequency. That's a very important concept, right? R does not depend on F. R does not depend on F. So what does it mean? That resistance, whatever may be the frequency, the resistance will remain the same. So it may be somewhere here, maybe. It can be anywhere, okay? It's not that it's going to be here. It depends on what is the resistance. It may be high, it may be low, okay, depending on that. But this particular point at which we are actually having the junction, where actually, the inductive reactance and the capacitive reactance are meeting, is going to give you the frequency, which is the resonant frequency. That's quite obvious, right? Because I said that at resonance, the inductive reactance and the capacitive reactance are equal. So they are equal at this particular point as per this graph. So that means it's my capacitive graph. Sorry, this is the graph that is going to, tell me the resonant frequency as well. So resonant frequency is my f naught. Okay, here we can write it down as f naught, resonant frequency. Okay, so this can be one graph. We can have different kinds of graph. We can actually have a graph between impedance and frequency now. Okay, impedance and frequency. So we are going to consider all the components together. Okay, so for that we already know what is my impedance. Okay, if you're basically considering a capacitive circuit or an inductive circuit, uh, you can have it as r square plus XC minus XL whole square. Okay, so we can have different kinds of condition here, or XL minus XC. So root over of r square plus XC is 2 pi FC minus, right, 1 divided by, okay, okay, anyway, let me write it down as XL minus XC, XL minus XC, same thing, 1 divided by 2 pi FC square. So if you want to actually plot a graph between now impedance and frequency, you have to check what happens with frequency and impedance value. Okay, so if f is large, okay, let's say f is very large. Okay, f is large. So if f is large, this quantity will be large, this quantity will be small, so you can ignore this and you can just take this value. So if f is large, z is going to be large because this is already there, plus you are going to take a large value of this, so z is going to be large, obviously. But what happens if f is small? If f is small, this will be small, but this will be again large because f is small, f is at the denominator, so z is again going to be large. This is large, plus again this is large, square term, so minus doesn't play any role, so z is going to be large. So that means z is going to be large, okay, for f, and at certain point it's going to be minimum. At what point? When both of them are equal, then only z is going to be minimum, but there is going to be no negative value. Okay, so that means what happens if I uh, plot a graph between f and z. Okay, f and z, we know that if f is small, okay, this is the small value, let's say z is large. If f is large, z is still large. Okay, and in between somewhere you are going to get the minimum value of impedance when f and this two factors are equal, XC and XL. So the graph would look like something like this. So this is my minimum value, and minimum means it will be giving me the resistance. Okay, that means that at this particular point you are also going to get your resonant frequency, because that is the minimum value, and that is how you can actually plot the graph. Okay, similarly we can actually plot the graph for current versus frequency as well. Okay, so we can again plot one more graph where we can actually have it as current versus frequency. Okay, let's talk about it in terms of peak current. So this would be just opposite to that, whatever we have plotted for z and f. Okay, okay, so what happens is that current will be more if z is less. Okay, and current would be less if z is more, right? So that means it's just behaving opposite to that of this z minus versus frequency curve. Okay, so that means here what happens is, if frequency versus current, z is less, okay, current is more. Okay, z is more, current is less. So what happens here also, that for lesser frequency, okay, if frequency is low, z is high. If frequency is high, z is still high. We have already seen it, right, in the relation. So if frequency is low, z is high. If z is high, current is low, so current is here. On the other hand, if the frequency is high, somewhere here, z is high. If z is high, that means the current is to be low, right? So again it will be low here, current. and in between there will be a space where you are going to get the maximum current. So that means for current, the graph is going to be something like this. Here, at resonant frequency, you're going to get the maximum current. So this is my resonant frequency, right? That's quite obvious because we know I naught is equal to V naught by Z. So if this Z becomes R minimum, the current would be maximum. So this is my maximum current, I max. Okay, so this can be another graph. These graphs will actually give you a lot of information about the system, okay, in a resonant graph. Okay, so that's it. Using these graph, you can also talk about the maximum power. Okay, I think maximum power is also quite clear to you already. I think this is something which I'd like to discuss again. Maximum power. So we have already seen what is my power or average power. We got it to be VRMS IRMS into cos phi. Maximum value of phi can be 90, so that's 1. So that means when we are talking about maximum power, I can write it down as V naught by root 2 I naught by root 2 into 1. So forget about that 1 now. This is V naught. V naught is I naught into R, because maximum is when Z is equal to R. So V naught would be equal to I naught into R. This is the maximum that you can have, maximum current, right? So I can simply write it down as I naught into R into I naught divided by 2. So this would be nothing but I naught square into R divided by 2. So in a circuit, you might also be asked, find out the maximum power, and the maximum power would be this. This would be your maximum power. I naught square R divided by